So we have, I didn't turn the recorder on, so briefly, this is what we talked about, please. So we have a resistor, we have a capacitor, and we have an inductor. This is based on a charge electric field, and this is based on a magnetic field. And they're all very useful in tuning circuits and transient circuits. We have a figure of merit called the capacitance, and the figure of merit is the total charge over the potential difference that causes the charge to develop. So I have a battery, and it will cause charge to accumulate, and at some point the charge will push back on an approaching charge with as much force as the battery is pushing it out. So we are fully charged. I have all positives on one side, I have negatives on the other, equal number. If I look at how the charging occurs with time, I find that I don't go linearly from having no charge to being completely charged. It's very easy to put the first few charges on, but it's very hard to put the last few charges on. So I get this so-called transient effect. And I pointed out we have this problem that we use C for capacitance, and we use C for coulombs, and F for force, and F for farad, and so on. It just gets a little bit confusing. We then did this example. Well, I tried to do it, but I messed up on it. So we have our capacitor, and we have our electrical potential, our voltage source. And so this voltage source drives the positives onto the top plate and the negatives onto the bottom plate. And when I am fully charged, I can have... when I'm fully charged, I have a capacitor which is 7, and never make this mistake, times 10 to the minus 12 farads. And I have 4 times 10 to the minus 3 volts. And so I want to know the potential, I want to know how much charge. So I say, well, C equals Q over delta V. That's the definition. Rearrange. Q equals C delta V. So Q equals 7 times 10 to the minus 12 times 4 times 10 to the minus 3, which is 28 times 10 to the minus 15 coulombs. Cool. Another type of question I can ask you on this is just looking at the relationship. What trace best represents the relationship between the charge on the capacitor, charge which has got the symbol Q, and the potential difference across the capacitor, which would be really delta V. And I say C equals Q over delta V. So let's rearrange. I want Q, so Q is equal to C delta V. That is that axis. That is that axis. So this is like Y is equal to the slope times X plus B. So this is linear. So my charge, the charge of fully charged increases linearly with potential. So that is that. Cool. Most common shape used for capacitors is the so-called parallel plate capacitor. Hold on. I ripped off my old TV set and I saw these things that look like these little candies. In fact, when I was a kid, my granddad and my dad were furniture salespeople. And big new furniture was the television and the radio. So they just got used to taking the back off the television and the radio and messing with them. And so they, you look inside and there's all these little candies. Some of them are resistors. Some of them are capacitors. The inductors are more easy to spot, but there are some inductors that are hard to spot. They're usually encapsulated. And there's different designs, but usually there's some kind of top plate and some kind of bottom plate, and there's some stuff in between. Maybe air, maybe waxed paper, maybe ceramic, maybe some noxious chemical, a wet chemistry type capacitor. But the plates are usually parallel. In these, which look like rolls, what they did actually was they took a long roll of aluminum or titanium or something. They took a long roll of wax paper or plastic or something. They took another long roll of aluminum. They then rolled it into a, and that's the end. So what you find on these is that you get an incredible surface area on these. Whereas these ones where you have plates, they're not so big surface area, so you'd better have a really good dielectric to get values that you want. You tend to want more capacitance. It's like you want more of what you want. Let's just think about two parallel plates. Most common type of capacitor is a parallel plate capacitor. It consists of two parallel conductors that are insulated or isolated from each other using an insulator or some type of insulator. One plate can be charged positive and the other plate can be charged negative. Oh, sorry about that. The capacitance of the parallel plate capacitor depends upon its cross-sectional area, not the area of the one plate and then the area of the other plate. It's the area of the gap, if you like. So you don't multiply the area by 2 because there's two plates. It's the area of the gap, because it's all about the gap. This is not about the metal. The metal just holds the charges. This is all about the gap. And so we say under those circumstances, then our capacitance is equal to, well, if I have more area, then I'll have more area to put the charges. More charge means more capacitance. So it makes sense that the capacitance increases as the area increases. And then it depends upon 1 over the D is the gap. It's not the diameter, it's the gap. So as the gap gets bigger, the electric field gets smaller. Now, does it go as an inverse square or does it go as an inverse? And usually when you're dealing with things that go out spherically symmetrically, it's inverse square. When you're dealing with things that go cylindrically, it's inverse. Well, this is linearly, so I guess, okay, inverse again. But you can kind of see D's got to be on the bottom, but should it be D or D squared? There's a little bit of thinking about that. And then we want the numbers to work out right, so we have a constant proportionality because A is in meters, square meters, and D's in meters. So to get farads, I've got to do something. So I have a constant proportionality, my epsilon naught. Supposing the gap is filled with something. Well, even in the room it's filled with air, but air, it turns out, doesn't have much effect. But if I fill it with paper, or I fill it with polyurethane, or I fill it with waxed paper, or I fill it with a wet chemistry, then that's going to have a different effect. And it turns out that I can characterize the effect of this dielectric by a figure of merit called my dielectric constant. And it's simply a number which is a multiplication factor. So if I put a dielectric constant in there that has a value of 100, I get 100 times the capacitance that I would do without it. Now, hold on. How do you get this capacitance? How do you get this thing? And this is the brilliance of the dielectric. So here's my parallel plate capacitor, and here's my battery source. So I'm putting on positive, 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 and negative, 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 negative. And I'm full. Can't put any more negatives on the negative side because they push back just as hard as I can push. Can't put any more positives on the positive side because they push back just as hard as I push. So I'm done. Not so fast. What I can do is I can put in here some kind of insulator. Now, I'm not going to draw all the atoms in this. I'm going to draw just one. I'm going to draw one atom. So I have an atom, and I have an atom. Oh, sorry, atom, 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 atom. I'm just cheating somehow, yeah? When it's neutral, the electrons surround the protons symmetrically. Everybody okay on that? Everybody here believes in electrons. Good. Should have some skepticism. It's just a visualization. So, all right, my somewhat skeptical positives symmetrically surrounded by my somewhat skeptical negatives, and I get a somewhat skeptical symmetry, I guess, yeah? But I know that positives attract negatives. I know that negatives attract positives. So that electric field surely must attract my electron cloud over here. And my positives will be attracted slightly to that side. And so now I'm getting what's called polarization. Polarization. And if you think about it, this guy that wants to join is faced by 6 positives that are saying, 1, 2, 3, 6 positives that are saying, you can't come here. But now there's these whole bunch of negatives, not complete negatives, but little bits of negatives. Somewhat close to these positives, so they kind of cancel one of them out. You know, it's 6 positives plus 1 negative. And on this side, we have 6 negatives, and, you know, these positives, they cancel that one out. 1 positive. Oh, well, that's only 5. So now you're allowed into the club. And now you're allowed into the club. And if I could make this even better, if the dielectric was even better, that one could get crossed out. So now I don't have 6, I don't have 7, now I have 8. And I don't have 8, 6 here, I have 8 there. And if this is even better, I can cross out that one. So now I have 9. It's still there, it's just its electric field effect. So my capacitance is the amount of charge, which is now 9 positives over the same old potential. So by using these fields to cancel each other, while the charge is still there, I'm increasing my capacitance. It might seem like cheating, and to some extent I suppose it is, but it's good. It works. All dielectrics have a maximum electric field strength that they can support. If I put 1,000 volts across here, I'm going to burn a little bit of a hole through my piece of paper. And you can see that sometimes. And once the hole is burned, there's a bit of a conductive path, and so the capacitor's shot. At the voltage greater than the dielectric field strength, dielectric begins to conduct. Cool. How big is the gap between the plates of a circular air-filled 3 microfarad parallel plate capacitor that has a radius of 4 centimeters? So let's draw it. So that radius is 4 centimeters. And I want to know how big the gap is. So I want to know, let's call this D. And so I need to say, well, what do I know? What do I need to know? Capacitance is equal to K epsilon naught A over D. So capacitance is equal to K epsilon naught. My A, of course, you'll be surprised at how many people will just put down the radius as A. But it's not. It's pi r squared over D. So then we say, okay, what do we know? How big is the gap? D is equal to K epsilon naught pi r squared over C. So D is equal to K, air-filled. For an air-filled capacitor, air-filled. K is equal to 1. That's 1. Epsilon naught. I cannot remember what epsilon naught is. Let's probably say it back here somewhere. Why did I say it? Is it there? No, I don't say it. I should know it. We'll figure it out. Epsilon naught. And pi is 3.142. And r squared is going to be, a lot of people put down 4. It's not. It's 0.4 squared over C. And C is 3 times 10 to the minus 6, because it's got to be in farads. So D is equal to 1. Can somebody look up what epsilon naught is? Permittivity. Permittivity of free space. Oh, 9 times 10 to the 9 times 4 pi. Is that right? Ke equals 1 over 4 pi epsilon naught. So epsilon naught equals
4 pi times Ke.
1 over 4 pi times Ke. So it's 1, so this is, epsilon naught is 1 over 4 pi times 9 times 10 to the 9 times 3.14, or pi, times pi, that's nice, that's going to go away, times 16 times 10 to the minus 4 over 3 times 10 to the minus 6. So my pi's go away. And so this equals 16 times 10 to the minus 4 over 12 nines, 108 times 10 to the 3, which equals about 0.16 times 10 to the minus 7, which is going to equal about 1.6 times 10 to the minus 8. Increase that 1, reduce that by 1. So it's going to be about 1.5, is that right?
Yeah, I got 148.
Yes. Good, thanks. So shame on me for not knowing those numbers, but you don't need to know them for the test. But that's how you do it. What catches most people out on that? I'll tell you, the thing that catches most people out is they're going to put down A, they're going to say, oh, I need a number for A, and they're going to put down 4 down for it. Or even 0.04, because they're not visualizing, they're just looking for, they have an equation and they're looking for numbers. And I'll gladly give you numbers to put into an equation. But if you don't draw the diagram, you're not going to get it right. And you're not being an engineer. Mathematicians put numbers into equations. Engineers visualize and then put numbers into equations. Okay, so we have a series of capacitors. Can you see how if I just connect these guys in parallel, the areas, the same gap, the areas are just adding? Can you see that conceptually? I might as well just put a little piece of foil between there and there, and it's just one big capacitor. And the area is whatever the areas add up to be. So if I have capacitors in parallel, I simply add up the capacitance. So capacitance parallel equals C1 plus C2 plus C3. You just add them. Can you see? Well, maybe not, but so that's a positive, and that's going to be negative, and that's going to be positive, and that's going to be negative, and that's going to be positive, and that's going to be negative. And can you see how I could basically get rid of that piece of wire, so I ended up with that, where if this is A, if this is A, that's B, that's C, that's D, that's E, and that's F. Those are the plates. This is A. This is B touching C. This is D touching E, and that's F. I can just shorten these pieces of wire. They're just conductors. No electric field to speak of in them. Long wire, short wire, who cares? Just touch the two plates together. Can you see how, because this is an electric field effect, the positive charges on one side of this plate will balance the negative charges on the other, so I might as well just take it away. AF with the bigger gap. Does that make sense? Okay, so what counts on this is the gap. And so 1 over the capacitance in series equals 1 over C1 plus 1 over C2 plus 1 over C3. Yeah? Can you see that? So you can work through the math if you want, but that's the take home. How do I know whether I am in series or parallel? If you've got several, now there is nothing, once you charge, there's nothing flowing in this. But if you imagine your finger, if your finger has several roots from one end to the other, if there's a junction, you're in parallel. your finger can only go through one way. That's in series. Okay? So you've got to be able to recognize, because what happens is we mix them together. What is the equivalent capacitance of a network that consists of a 3 nanofarad capacitor, a 4 nanofarad capacitor, and a 12 nanofarad capacitor connected in parallel? So this is 3 nanofarads, this is 4 nanofarads, and this is 12 nanofarads. C parallel equals C1 plus C2 plus C3. C parallel equals 3 times 10 to the minus 9 plus 4 times 10 to the minus 9 plus 12 times 10 to the minus 9. C parallel is equal 19.
You said minus 9.
I know. 19 times 10 to the minus 9. I'm rushing. Whenever you rush, you pay a big price. Just add them together. What is the current capacitance of a network that consists of a 3 nano, a 4 nano, and a 12 nano in series? Oh, now I'm going to have to earn my money. 3 nanofarads, 4 nanofarads, 5 nanofarads. 1 over C parallel equals 1 over C1 plus 1 over C2 plus 1 over C3. 1 over C parallel is equal to 1 over 3 times 10 to the minus 9 plus 1 over 4 times 10 to the minus 9 plus 1 over 5 times 10 to the minus 9.
It's series, not parallel.
Oh, series, you're right. I'm rushing. Man, thank you. What would I do without you guys? Like,
The last one is 12.
last one is 12. I'm rushing. Just a little parallel to the one side for a minute. 1 over 3 plus 1 over 4 plus 1 over 12. That's going to be 4 over 12 times 10 to the minus 9 plus 3 over 12 times 10 to the minus 9 plus 1 over 12 times 10 to the minus 9, which equals 4 and 3 makes 7. That makes 8 over 12 times 10 to the minus 9. So CS is equal to 12 times 10 to the minus 9 over 8. You've got to flip it, which equals 1.5 times 10 to the minus 9 farads. Most common mistake on those two, they either get them backwards, they think it's parallel when it's series, or they think it's series when it's parallel, or on the series one, they don't flip it at the end. So they'll give me an answer which is basically, 0.66 times 10 to the 9, because they don't flip it. And they don't flip it because they're not writing down an equation, and they're not writing down an equation because they're just putting numbers down. So really do try and write in complete sentences. I just want to see how far we're going. I'm going to draw a line. Oh, I'm not going to draw a line. We're fine. So, what to do? What are you going to do? Are you going to try and add the 3 and the 12 together, or the 2 and the 4 together? Where would you think we should start? And why? Why not the 3 and the 12 and then the... Because, no, it's not because they're parallel. It's because they're, like, unambiguous. These guys, if I try to add those 3 together, it's not going to work. And those 3 together, it's not going to work. But those 2 are going to work fine. Yeah? So I go, okay. So let's have a look. This is 2, and that's 4, and that's 3, and that's 12. So the first thing I'm going to do is say, are they in series or parallel? Parallel, so CP equals C1 plus C2. So this equals, because they're parallel, I go 2 plus 4 equals 6. So 1, 2, 6, and 3, and 2. 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3. 1 over CS is equal to 1 over 6 plus 1 over 3 plus 1 over 2. 1 over CS is equal to 1 over 6 plus 2 over 6 plus 3 over 6, which equals, oh man, is that right? 6 over 6? 6 over 6. You got to flip it. Bad example. Is equal to 6 over 6, which equals 1 farad. Let me just double check that. 1 over 6, yeah, that's right. 1 over 6 plus 1 over 2 plus 1 over 4. Oh, no, 1 over 6 plus 1 over 2, 3 plus 1 over 2. So that's 3 over 6. That's 2 over 6. Yep, that's right. Okay. I could play around with it. I could give you, 1, 2, 3, and then do that. I could even do that, Then you do the series bit, then you do the parallel bit, then you do the series bit.
And then you add
You do the series bit, you do the parallel bit, then you do the series bit. Like I did parallel, then I did series. This is a 3-step problem. Okay? And so on. The book loves to give you things like this. And if we had a lot more time, I'd be fine with that. But we don't have a lot more time. So I won't go there. But just for those, especially doing electrical engineering, that's where they like to go. They like to just see, can you play with these circuits? We'll do more on circuits later. So I'm more inclined to do something like that when we're doing resistances. At the moment, we're just trying to get capacitances down. Okay, 2 last little bits. The charges cause an electric field. And you don't get something for nothing, so that electric field costs energy, but it stores the energy that it costs. It's like you put a can of beans on the shelf, it takes you work to put the can of beans on the shelf, but if the can of beans falls off the shelf and hits you on the head, you get all that work back, It's like, unless there's friction in mechanics, you can keep the energy you play with. Unless there's resistance in electricity, you can keep the energy you play with. So it's a fair question, how much energy can I store in a capacitor? The answer is not very much. You're much better off using a wet cell, or a dry cell. Use a battery if you want to get electrical energy, or better still, a generator. But don't, as a first choice, store energy in a capacitor. There's some times where if you want to store it for a little time, and you're at very high voltages, for example, in some very high voltage transmission electron microscopes, they have big capacitors there, because you just want to store energy for a little time. But by and large, don't store things. You're better off using chemistry to store charge, to store energy. But let's see if we can figure out how much we store. Well, we know, consider the charging of a capacitor. As the charge increases, the potential difference across the capacitor increases. So I need to talk a little bit. In fact, I'm going to do this. And I'm going to stop here, because there are some important points, and you can still do all the rest on capacitance. So I don't want to rush this bit, though, because I think it's really valuable. So let's stop that there.